Lesson: AI techniques for malware behavior analysis. Artificial intelligence is revolutionizing the field of cybersecurity, particularly in malware behavior analysis. This transformation is pivotal for professionals preparing for the CompTIA CySA certification, specifically in the section on AI for endpoint security. AI techniques offer actionable insights and practical tools that can significantly enhance malware analysis capabilities. By leveraging machine learning algorithms, neural networks, and advanced data analytics, cybersecurity professionals can detect, analyze, and mitigate malware threats more efficiently. Machine learning, a subset of AI, plays a crucial role in malware behavior analysis. Supervised learning algorithms, such as decision trees, support vector machines, and random forests, are commonly used to classify and detect malware. These algorithms are trained on labeled datasets containing features extracted from known malware and benign files. For instance, by analyzing the opcode sequences, system calls, and network behavior, these algorithms can identify patterns indicative of malicious activity. A practical tool that utilizes these techniques is Microsoft's Advanced Threat Analytics, which applies machine learning to detect suspicious activities by analyzing user behavior and identifying anomalies that deviate from established patterns. This approach allows for quicker detection and response to potential threats, as demonstrated in a study by Sachs and Berlin, which highlighted the effectiveness of machine learning in identifying previously unknown malware variants. Unsupervised learning is another AI technique employed in malware behavior analysis. Unlike supervised learning, unsupervised learning does not require labeled data. It is particularly useful for detecting zero-day threats and advanced persistent threats that may evade signature-based detection systems. Clustering algorithms like k-means and hierarchical clustering can group similar behaviors, allowing analysts to identify outliers that may represent novel malware. A practical application of unsupervised learning is found in the tool Malware, which clusters malware samples based on their behavioral profiles to identify new malware families. By clustering similar behaviors, security teams can prioritize their analysis efforts and improve response times. Deep learning, a more advanced form of machine learning, offers further capabilities for malware behavior analysis. Convolutional neural networks and recurrent neural networks have shown promise in detecting malware through static and dynamic analysis. CNNs, traditionally used in image recognition, have been adapted to analyze byte sequences in executable files, thus identifying malicious patterns. RNNs, known for their ability to process sequential data, are effective in analyzing API call sequences and other temporal data generated by malware during execution. Deep learning models can automatically extract features from raw data, reducing the need for manual feature engineering. This capability is exemplified by the success of a deep learning framework developed by Hardy et al., which achieved high accuracy in detecting malware by analyzing API call sequences. Despite the effectiveness of AI techniques, challenges remain in their implementation. One significant challenge is the need for large, high-quality datasets for training machine learning models. The lack of labeled data can hinder the performance of supervised learning algorithms. To address this issue, cybersecurity professionals can leverage data augmentation techniques, such as feature transformation and synthetic data generation, to expand their datasets. Additionally, organizations can collaborate with threat intelligence platforms to access shared datasets and threat intelligence feeds. The use of frameworks like MITRE ATT&CK can also aid in mapping observed behaviors to known tactics and techniques, providing valuable context for analysis. Another challenge is the interpretability of AI models. Deep learning models, in particular, are often considered black boxes, making it difficult for analysts to understand the decision-making process. To address this, researchers are exploring techniques such as attention mechanisms and model explainability tools to provide insights into how AI models arrive at their conclusions. For example, the use of LIME can help interpret the predictions of complex models, enabling analysts to validate and trust AI-driven decisions. AI techniques also offer actionable insights for incident response and threat hunting. By automating the analysis of large volumes of data, AI can reduce the burden on security teams and allow them to focus on high-priority tasks. Automated threat hunting frameworks, such as CrowdStrike Falcon and IBM QRadar, leverage AI to continuously monitor network traffic, endpoint activities, and user behavior for signs of compromise. These tools use AI-driven analytics to correlate events, detect anomalies, and generate alerts for further investigation. In practice, a case study by Symantec demonstrated how AI-powered threat hunting reduced the time to detect and respond to threats by 50%. Furthermore, AI techniques can enhance endpoint security by providing real-time protection against evolving threats. Endpoint detection and response solutions, such as Carbon Black and Sentinel-1, incorporate AI models to monitor endpoint activities, detect suspicious behavior, and block malicious actions. By analyzing file attributes, process behaviors, and network connections, these solutions can identify and mitigate threats before they cause harm. For instance, Sentinel-1's AI-driven solution demonstrated its ability to prevent ransomware attacks by detecting and terminating encryption processes in real time. To effectively implement AI techniques for malware behavior analysis, cybersecurity professionals must stay informed about the latest advancements and best practices. Continuous learning and skill development are essential to keep pace with evolving threats and technologies. Online courses, industry conferences, and research publications provide valuable resources for gaining knowledge and staying updated on AI applications in cybersecurity. Collaboration and information sharing within the cybersecurity community also play a vital role in enhancing AI-driven malware analysis. Threat intelligence sharing platforms, such as VirusTotal and ThreatConnect, enable organizations to share threat data and collaborate on identifying and mitigating emerging threats. By participating in these platforms, security teams can gain access to a wealth of information and leverage collective intelligence to improve their defense strategies. In conclusion, AI techniques are transforming malware behavior analysis by providing powerful tools and frameworks for detecting, analyzing, and mitigating threats. Machine learning, unsupervised learning, and deep learning algorithms offer actionable insights and practical solutions that enhance endpoint security. By leveraging AI-driven tools and adopting best practices, cybersecurity professionals can improve their ability to detect and respond to malware threats, ultimately strengthening their organization's security posture. Continuous learning, collaboration, and the use of advanced AI techniques are essential for staying ahead in the ever-evolving landscape of cybersecurity.